Hi, everyone. Thank you for attending today's webinar, Principles of PV Soiling Measurement. I'm Kelly Pickerel, Editor-in-Chief of Solar Power World. And before we get started, I wanted to go over a few items. You can download the slides and any additional resources for today's presentation in the resource window on your screen. We will have a Q&A at the end of the webinar, so please submit any questions in the Ask Question window. If we do not get to your question, our presenters may reach out to you afterwards. You can also expand your view of the slides by using the icon in the top right corner of the slide widget. All the boxes on your screen can be moved and resized to meet your preferences. And finally, if you are watching this webinar on demand, you can still use all of these features, including sending questions to the presenters. If you experience any issues during today's webinar, try refreshing your browser tab. If you continue to have problems, try closing other apps and browser tabs that you may have open, and you can click Help in the top menu for more troubleshooting steps, or you can ask our producer for help in the Ask Question widget. So let's get started with today's webinar on PV soiling and measurement tests. I'd like to thank Kip and Zonin for sponsoring this presentation. Today we are going to hear from Josh Horse and Michael Gostein from Kip and Zonin. So now I will turn things over to them to get us started.
All right, hello everyone. Welcome to Principles of PV Soiling Measurement. Without further ado, we'll get started. So the agenda for today will, at a high level, talk about what is soiling, why do we measure it, what are the different techniques to measure soiling, and we'll dive deep into each methodology, including reference cell pair, optical, and reference module pairs, with a focus on in situ module IV. Then we'll finish up with questions and answers. So what is soiling? Soiling is often a misunderstood term. We usually point to dust accumulation on solar panels, but it can also be snow, pollen, any other kind of biomaterial that blocks light transmission to the solar panel and produces power on the panel. So the key takeaway is that it's a major loss factor in a PV power plant, and we'll touch on that in the next few slides. But what is non-uniform soiling? So this is something that maybe we've heard of, maybe we haven't. It's the concentration of soiling on particular cells within the module, often the edge. This causes a greater power loss than if it was uniformly distributed along the module. It can be caused by rain patterns, wind patterns, prevailing winds, and gravity pushing dust or other particulates to the side of the panel. It can only be measured by IV curves, power measurements on actual modules. In a bonus, if you actually measure on PV panels that are string connected, that simulates or reflects the way wind pattern actually deposits dust onto that panel. So why do we measure soiling at all? It's a requirement of the IEC 61724-1 spec governing PV performance monitoring. There is a very particular reason for that. It is one of the greatest loss factors in a PV power plant, often cited in the top 3 behind temperature losses. We usually point to resource assessment, so fine-tuning your financial model to determine how much energy you'll get out of your power plant, how much loss do you have due to soiling in the future. We also typically look at optimizing cleaning schedules. When do you get a return on investment? When you clean the panels to increase the power output of your plant. But a nuanced approach or reason to measure soiling would be to isolate underperformance metrics or underperformance issues during plant commissioning or ongoing operations. If you don't have a high degree of certainty for your soiling measurement, then that cascades to other derate factors in the uncertainty surrounding those. We'll dive a little bit deeper into that nuanced approach. So the key is if you don't measure soiling, then you don't really know what's going on in the rest of your plant with regards to the underperformance. For performance tests specifically, and most specifically a short-term test, in the US we call it capacity tests, a failed capacity test means a lot of financial damages to the construction company when they hand it off to the owner and operator. However, soiling is oftentimes outside the scope of that test because it's a natural phenomena that's uncontrollable in a lot of ways. So if you have a high degree of certainty for your soiling measurement, that can allow you to meet the tolerance band of that test and prove to the owner and operator that your plant was designed or constructed in the way that it was designed before you constructed the power plant. If you don't measure soiling at all or assume some kind of baseline rate like 2%, and it's actually a 4% loss, then that bucket has a high degree of error and you may not pass that test. So for capacity tests, other performance tests, it's extremely important to measure soiling to a high degree of certainty. And that's at Kip and Zonen. We have a lot of experience with that. So does Michael Ghosteen. If you want to talk about that offline, we certainly can. And again, determining when you have a positive return on investment from cleaning panels. So when does the power generation gained from cleaning the panels outweigh the cost of cleaning those panels? And with the measurement of non-uniform soiling, which often has a greater effect on power, that's where those kinds of measurements in situ module IV becomes very important. So this is an example of a sawtooth pattern, typical soiling measurement pattern that you may see in a power plant. And of course, being in compliance with IEC 61724-1 is very important. If you want to meet the Class A standards as a company in an offering, then you have to measure soiling, along with all the other metrics, wind speed, module temperature, irradiance being, of course, the most important. So let's hop into the different soiling measurement techniques, and we'll talk about each one specifically in detail. To start, we wanted to characterize the different techniques into really two different buckets. We have standalone sensors, which would be an optical or reference cell pair system. Those are measuring soiling on devices near the panels. It's not an integrated system where you're measuring the panels within the array. If you want a direct measurement on the power loss due to soiling, including the effects of non-uniform soiling and module degradation, we would always recommend an in situ module IV system. However, I'm going to go back to this slide real quick. And we'll talk about after this poll question, different reasons why you would select one versus the other with respect to each unique customer need. But I do want to differentiate between standalone sensors that are measuring soiling on something nearby versus an integrated system that's measuring soiling on a panel. So here's a poll. We'll just stop here and let you all respond to it. What soiling measurement techniques do you most often use at your solar projects? And we haven't talked about each one, but I think these are generic enough for you to choose. Reference cell pairing, being two reference cells, a clean and dirty pair. It measures the difference between the two, outputs a soiling ratio. Optical, Mars or Dust IQ sensors, and reference module pair would be a comparison of a dirty and clean solar panel. The Solar Power World team, how long should we wait on this poll question?
I'd say give it about 20 more seconds or so. Looks like we have a good amount of people submitting responses already.
Fantastic.
All right. I think you could probably move forward if you'd like.
Well, would you look at that, an even split. So very interesting. We'll go through each one in depth, each methodology, and then maybe that will validate what you use, and maybe you'll look at some other systems as well. All right, this is the slide I want to focus on mostly in this presentation. Each solution has trade-offs for different customer needs. We can simplify the selection of a soiling sensor really on one axis with different terminology or characteristics on both sides. So if you look furthest to the left, we say less maintenance, lower uniform soiling. If you have a basic power plant that has a relatively low soiling and you do not have on-site staff to clean things, that's a big difference between an optical sensor and the rest of the sensors. Optical does not require any maintenance, washing, calibration. They're plug and play, simple communication protocol and setup, standalone sensors. So if you have a C&I power plant, for instance, you don't have on-site staff, this would be the go-to option. The rest of these sensors require some sort of maintenance, as in washing things or refilling tanks. In any case, you have to go to the site and do something. In the middle, we have a reference cell pair. This is more the traditional means of soiling. From my experience, this is kind of how the industry for soiling measurement started. It's very basic. It's two PV reference devices, those being reference cells that measure irradiance. You have a clean and dirty pair, and you simply measure the difference between the two. Often there's integrated washing systems for our products and others where these are allowed to automatically calculate that soiling ratio, do averaging techniques, and spit out a output to the data logger. In a way, these are a little bit more representative to power loss on the modules because you're using PV reference devices that carry the same incident angle modifiers, same construction as the PV module glass, same material, similar spectral matching to crystalline silicon modules. Now on the far right, we have our premium, most direct way to measure soiling, which would be in situ module IV. We discussed how IV curves can measure non-uniform soiling, so this is in a whole different class from the others. We'll also discuss general reference module pairs in this presentation and kind of differentiate the IV curve-based systems versus ISC-based systems. But these require oftentimes a little bit more maintenance, cleaning full-size panels and such. So Kip and Zonin has really a solution for any of your customer needs. At this point, we kind of cover all of our bases for different soiling measurement methodologies, and we're your partner to help select something for you. Feel free to talk to some of our sales managers about fine-tuning a selection for your particular need. So a reference cell pair is, I would say, a traditional means to measure soiling. It's the most common from what I've seen, except our poll said it was pretty much evenly split. It compares the irradiance off a PV reference device, a PV reference cell, between a clean and dirty. You have the benefit here of also getting a plane of array irradiance measurement if you want to couple that against your pyranometer. And oftentimes they come with integrated systems that wash those reference cells automatically. These reference cells are small, so a simple water spray is able to clean them easily. You can hand wash much easier a cell versus a module. They can also be used in conjunction with our reference module-based systems, which we'll touch on a little bit later. So a reference cell pair, it's pretty intuitive. I won't hammer it again, but it's a comparison between the clean and dirty cell. Now, why would we use an integrated cell washing system? Where one, it aggregates the data and performs automatic calculations, so it's a smart sensor. It can do any kind of averaging. There's many different averaging techniques, from daily averaging, real-time measurements of the soiling ratio, rolling averages, etc. And obviously, they perform automatic washing with capacities varying from 3 months to a year. So that minimizes the maintenance on your staff needed to actually obtain an accurate soiling measurement. Here's a quick look at our cell wash system. Other systems would probably be very similar. They are, at its most basic form, a water tank, a pump, and a controller to aggregate the data and send it out to your SCADA system via Modbus RTU or RS485. Our system has a unique benefit in that it has an integrated battery that trickle charges when it's not in use. So we can use standard met station power supplies with ours. Standard power draws about 1 to 2 watts. Max is about 8 watts after spray for about 90 seconds. but these assist in the washing of those reference cells to minimize the maintenance needed to get a soiling ratio measurement. Oftentimes in Kip and Zona, we offer different mounting configurations. Long story short, reference cells are pretty easy to mount, pretty easy to manage on your solar site. They're off your array. They could be mounted to your single axis tracker torque tube, but there's cables that connect your reference cells to the system, and then a water hose that sprays water. All right, let's go into optical. So optical sensors are also standalone, but they have the huge benefit of no washing, no maintenance, and some have no calibration. So I'll state that again, no washing and no maintenance needed. They're optimal for both CNI and utility scale solar projects. We've sold plenty to both. Where on-site staff is limited, these devices really reign due to the fact that you don't have to clean anything. So they're very simple. They spit out a soiling ratio, just plug and play. So we'll talk about each of our optical sensors. First one being Mars, that was developed by Atonometrics prior to the Kip and Zonin acquisition. It has an internal camera that's within the device. It's focused on the top surface of that glass. So any soiling that deposits on that glass, we actually capture in a physical image, and then the device automatically does an algorithm that pretty much counts the shaded pixels. It's much more complicated than that, but at a basic level, that's kind of how you can understand it. It performs one soiling measurement per day at sunset. The reason for that, I'll touch on that in the next slide, but it needs optical light conditions due to the nature of the device. It needs to look at the sky to have diffuse light conditions where the image analysis is optimized. Here's a breakdown of how it works. So again, as soiling deposits on that glass, we simply read it. Whatever falls on that glass, if it casts a shadow on the image sensor, we'll read that. So with that, there's no calibration. It's calibrated in our lab prior to shipment. It's really just plug and play. It just works. Here's a quick snippet of some data we had from a few years ago. This uses the old Mars unit, but the principle still applies. It's the same soiling measurement algorithm we use in our new version, but you can see it tracks very well to a reference cell pair. Same kind of principle here. This is our new Mars. Again, it's the same as the old one. This time we compare it to a dirty and clean PV string. So this was a study done in Qatar where we compared a couple of our different soiling measurement configurations, but we got a very good data set of Mars. You'll see in this middle section here, there's a fallout in the experimental procedure. That's why there's a divergence, but you can see it tracks it very well. If you have any questions, we could talk about it offline. But it bounces right back here when both are cleaned again, the control and the Mars unit. Due to the nature of the Mars technology, it requires a clear view of the sky. We offer different mounting sets to accommodate that, but it does need to have a full view of the sky without any obstruction from, say, trees or other racking. So usually it's mounted plane of array with your panels. It could also be mounted on a Met station cross-arm tube if you'd like at some kind of angle of inclination. Many different mounting. The takeaway here is these standalone sensors, they're easy to mount, right? It's a small box as compared to a kind of integrated module system. And we'll touch on Dust IQ. The first thing to note is that the Dust IQ and the Mars are really two different sensors. They're different methodologies. We call them both optical, but really they have a completely different measurement principle. Mars is a camera-based. Dust IQ works with an internal photodiode. It measures active reflected blue light off the glass, and when the signal is increased, that means greater soiling. And it has 2 measurement points, as you can see by the blue circles on the device. For Dust IQ, it provides continuous data. So minute by minute, it clamps easier to module frames. So if you have automatic cleaning robots on your site and you want to assess the performance of those, the mounting clamps enable it to better reflect, or be in the plane of array of the module. So this is a quick snippet of how Dust IQ works. With an LED light, when it reflects off dust, it reflects back onto the photodiode, and we take that as a measurement. So rather simple and straightforward, but very different from the Mars. Here's a quick data set of Dust IQ, just presenting the 2 different measurements that Dust IQ provides. It could be used for data redundancy or some level of soiling on the top and bottom surface. Contact us to learn more. So yeah, Dust IQ can be mounted easily to the module frame. So here's a slide I think we're all excited to see. Really, Mars and Dust IQ have unique feature sets for different customer needs. If I can point one thing to you, it would be the calibration versus the frequency. So Mars doesn't require any localized calibration. It doesn't depend on dust color. It's just measuring the shadow of any dust that is on top of that glass window. So for that reason, the elimination of calibration makes it effective, and also its dependency on changing dust colors throughout the seasons makes it a valuable case for Mars. Now for Dust IQ, it performs continuous measurements minute by minute. So if that's a requirement on your site, then Dust IQ may be right for you. Again, I said this a couple times, but the takeaway here is that they're really 2 different devices. Even though we bucket them as optical, they're different methodologies. One's camera-based, one is a reflective-based. But really, from a requirement standpoint, they essentially serve the same purpose. They're both no maintenance. They don't require any kind of excessive setup. There's no water involved. So for simplified approaches on measuring soiling at your PV power plant, optical makes a strong case for it. Moving on to reference module pairs. So these measure soiling on full-sized modules. They could either be in situ or offline being modules that are outside of the string on a separate platform, or maybe on a torque tube extension. A key differentiation I want to make in the next slide, talk about it here, is the difference between Pmax, maximum power point, and ISC, or short circuit current measurements on full-sized modules. IV curve-based systems, such as RDE 300i, and there's some others on the market, have the ability to measure that non-uniform soiling due to IV curves. They have the ability to connect to string-connected modules, which are more representative measurements. And they also have the ability to monitor degradation and even irradiance. So I have a teaser for you at the end of this presentation where we show a little bit of degradation data as well. So there's a key difference I want to state right off the bat between Pmax and ISC-based reference module measurements. Pmax is measuring power. At the end of the day, we want to measure the power loss due to soiling, as opposed to just the short circuit current, which is closely related to power loss, but doesn't paint the whole picture. ISC measurements on modules are probably more closely related to reference cell pairs than Pmax or IV curve-based systems. IV curve-based systems, which measure Pmax, have the ability to measure non-uniform soiling IV curves, degradation monitoring. So there's a lot more applications we can use with an IV curve-based system. Maintenance is going to be the same if you have what we call our module configuration, where you have to clean a full-sized panel. So we'll hop into a poll here. How often have you seen the non-uniform soiling phenomena at solar projects? And then I'll give my take on what I've seen, and then we'll talk about the reasons why you would want to measure non-uniform soiling, because the data suggests it's quite a big difference. It makes quite a big difference. Give it just a few moments. All right, so here's the results. Yes, I would typically see, I've personally, because I've been involved in RD300i installations, which is a bit biased because that would suggest there is some form of or fear of non-uniform soiling, but about half the sites I've seen, typically we see at high level at maybe 25 to 50%. But this is a good lead in to us discussing why you need an IV curve-based soiling measurement system to measure this non-uniform soiling. The reason being, simply PMAX measurements are more accurate than ISC measurements when there is non-uniform soiling. So this is a simulated study that Michael had made many years ago, comparing portrait and landscape-based modules or oriented modules, where non-uniform soiling is present on the lower edge. So in particular, we can look at the landscape orientation. The soiled area is covering about 3.3%, but due to its position on the module, ISC measurements may only read 1%. However, we want to measure the power loss due to soiling. PMAX does that, and you actually can get up to a 10% power loss. And we'll show some data to back up that claim. Often without IV curve-based systems, you could be missing 4% soiling loss that is actually occurring on your power plant in these kind of extreme cases. So our RD300i measures soiling on in situ modules as well. We've already discussed what non-uniform soiling is, and from the poll, it looks like it happens quite often, which is my experience as well. But I want to hone in on the term in situ or inline for a moment. This means it can be connected to string-connected modules. So modules producing power within your array connected to your inverter. RDE300i has the unique ability to do this by switching between measurement and reconnectivity between the string for that particular module. And we'll talk about the kind of the IV curve capabilities a little bit here too. Reference module systems that don't measure IV curves still have a better, more representative measurement than maybe a smaller cell, because it captures the full soiling pattern that occurs on that module. But without the non-uniform soiling measurement and the in situ capabilities, you don't get the full picture. The entire system is not reflected in what you actually want to measure, which is, again, power loss on real modules producing power within your array, within the row, and reflective of how the majority of your panels are connected at the power plant. Real modules equal more representative indirect measurement. And here's a look at some data just on 2 standalone modules from a test we did a few years ago. You can see that the ISC and PMAX measurements track quite well against each other, right? Until you get to a scenario as shown in figure B, which is this pattern of non-uniform soiling. You see that the measurements diverge quite substantially, up to maybe 5 or 8%. So that's why it's very important in these scenarios to be able to measure this non-uniform soiling behavior. And again, this ties into the performance tests as well. If this kind of soiling occurred on a short-term capacity test and you didn't have visibility into it, then there's a high risk that you might fail that test. Then when the modules are clean, the data jumps right back up. We'll have one more data set here. This is a bit more recent. This is from that same Qatar study done with Mars. But you can see that in the presence of non-uniform soiling, even a light bit of concentration of the soiling along the lower edge can cause a change in that measurement. And now we can dive deeper into some of how the in situ reference module-based systems work. They're connected within the array. One particular note here, without going too far into the weeds, would be our requirement that the reference module, the one you select for measurement, should be at least 5 from the end of the row. If you want to know a detailed reason of why that is, we can chat with Michael Ghosteen offline. He's done a lot of research on this. Non-uniform irradiance on the rear side of the panels can affect the measurement if you're comparing one versus the other. If one module is closer to the end of a row and sees more illumination from ground cover, then that can affect the measurement. So it's always important to select modules that are within the array, closer to the center, where both modules see the same rear side irradiance, where the ground cover is similar, the racking is similar, etc. Last thing I'll note on our product specifically is, in this case, we have 2 RDE 300i units. They talk to each other privately through a private network. All data is aggregated in what we call our leader unit. And all the calculations are done automatically. So it's only one Modbus address that you have to configure from your data logger's point of view. In these systems, just to reiterate, reference module-based systems require manual cleaning of a full-sized panel. So these kinds of systems are going to offer the most accurate means to measure soiling, but there can be a bit of process-dependent error if your cleaning schedules for that particular module deemed clean is not actively cleaned on a regular basis, and you don't have timestamps of when those are cleaned. And I'll talk about how we improve that here in a couple other slides. So real quick about our module IV curve-based systems. We can talk more in detail, probably in another meeting would be better for the audience. But we're able to measure IV curves once a minute by rapidly disconnecting that particular reference module, performing the IV curve, and then reconnecting it to the string. So this doesn't have an effect on the string inverter. We validated this study. We can do IV curves once a minute and then fill in that data with ISC and VOC approximations to scale the IV curve with what's needed. So that's an inside look of how this technology works. They're typically mounted, they're mounted actually always to, say, a vertical pile underneath the solar racking. So a couple PV cables. Our device includes a backup module temperature sensor with every unit. to compensate different soiling ratios and performance indices for temperature. And we do offer a mounting bracket for this. We're coming up close to the end of the presentation, so please bear with me. One thing I want to discuss is what we call normalization or field calibration. This process was required for both reference module and reference cell-based systems. This is due to different variations in the output, all else being equal. Even if a module comes from the same factory, the same lot, they can still produce slightly different power. And we found that they can produce up to 5% different power than what the module nameplate sticker states. So to achieve a high level of accuracy for these measurement systems, we have to normalize these two sensors, being the panels, together to drive the soiling ratio to 0. How do we do that? We clean both modules. This is the same for cells. You would schedule a day to do this normalization process. You'd clean both panels, and then you would do a procedure in what we call our configuration manager to drive that baseline soiling ratio to 1. And we do recommend that we renormalize once per year to address uneven degradation on the modules. Last thing I'll note on this slide is there are ways to retroactively normalize the system with external analysis. So if you're doing a capacity test and you can't clean the panels because you need to have that soiling on the panel to make the measurement, there are ways to do that and get a measurement without doing this normalization process with some external calculations. So addressing the kind of process-dependent error of cleaning a full-size module, which is obviously labor-intensive, we offer a module cell-based systems. These systems work by comparing a dirty reference module, which is the most important measurement, compared to a system of clean reference cells. These reference cells can be manually cleaned, or you could integrate our cell wash system to automatically clean them. But with the normalization process, we're able to directly compare the module's power versus the front and rear side irradiance of the reference cells. So with a system like this that has automatic washing, you don't have to worry about washing. You don't have to worry about timestamps when your people actually went to wash the modules. This system offers a lot of advantages compared to module, but as you can see here in the data, at the expense of a little bit of uncertainty, I would still claim that it's the second best means to measure soiling. But rear side irradiance can cause some non-uniformity. But as you can see really in this chart here, and if you zoom in on the y-axis, that soiling ratio is relatively low, which was good for this test. Because what we want to see is that the performance index between a module-based system and a module cell-based system are comparable. So in this data set, we can clearly see that they're very comparable. Okay, last few slides here. Just a quick teaser on degradation, because I know that's very important for our audience and people I've talked to. This is specific to IV curve-based measurement systems. You can do same degradation measurements with handheld IV curve tracers, but the benefit of our device is it's permanently installed and can have a continuous stream of measurements. So why do we do that? Well, relating this back to soiling, non-uniform soiling can actually cause long-term degradation. So a system or a device that can measure both simultaneously can effectively account for some of these unknowns, soiling and degradation. And if we want to talk about this data set, we can sure do so offline, but this is a study validating that our IV curve-based system can indeed measure degradation. And we see a pretty heavy decrease in the rating of the modules over a quite short period of time. So while this was occurring, we were able to do a study to measure both soiling and degradation simultaneously. So that's a major benefit of IV curve-based systems is all these unique additional applications that it can do, having an integrated system. And lastly, ISC and IV curve-based systems can measure effective irradiance. The calculation or formula is down below on the left. These do require module calibration. Again, this is an application outside of soiling, so I won't spend any time on it, but I did want to make you aware that there are plenty of applications that you can do in addition to soiling measurement with an IV curve-based system. So thank you very much. Solar Power World team, that's the last slide for me. So without further ado, I'll take the stage.
All right, thank you, Josh, very much. We are now going to enter the Q&A portion of the webinar. So you can continue to submit questions in the Q&A box on your screen. Got a lot of really great questions, so we'll kick it off. Josh, to you. Which soiling monitoring technology provides the best accuracy to cost ratio?
Well, I think we need to differentiate between non-uniform soiling and regular soiling. So if you have non-uniform soiling on your power plant, the value of using an IV curve-based system is very high. So you'll absolutely get your return on investment with a system like that. If you have a rather uniform or low soiling values on your power plant, say somewhere in Northern Europe, then maybe an optical sensor or simple reference cell pair might be appropriate.
Okay, perfect. Next question, about how many sensors would you deploy at a solar site per megawatt or per acre or some other ratio? How do you figure that out?
There's a specification that states the number of MET stations per megawatt, and we typically follow the same thing for soiling measurement stations. So it's about 3 or 4 per 100 megawatts, and I think that number might be increasing in the new IEC 61724 specification. So to keep it very simple, say 4 per 100 megawatts.
Okay. Okay, next question is, what uncertainty is acceptable for operational decision making?
Well, I mean, if you're trying to pass a performance test, then I would probably want it to be as low as possible. If you want to be able to relay the accuracy to meet some kind of financial or design obligation, RDE300i, the module configuration will be absolutely the highest accuracy device on the market. So if you need to measure non-uniform soiling, RDE300i stated uncertainties, somewhere in the range of 0.5%, outside of process-dependent error that I discussed. And then the other devices, they're stated on their data sheets. We could talk about that more offline.
Okay, gotcha. Okay, our next question, it has a little bit of a backstory to it. So it starts off, soiling measurements have become quite accurate when taken at a single point using dedicated instruments, but the challenge is how to extrapolate those point measurements across large-scale solar plants covering several hectares. So what approaches are currently being developed or implemented to address this challenge?
From what I've seen, the number of soiling stations is aligned with the MET stations because you need to have a way to collect the data. But if you have a particular case where there's a dirty road picking up dust, then I'd recommend placing an additional station near that road. So if you think about your power plant as having a heat map of soiling, you'll want to distribute them normally across the power plant, and then maybe focus a couple additional sensors where you may have a greater concentration or higher degree of soiling. But really, it's still up for debate. Ultimately, the developers, the owner and operators with all their data from existing sites would probably be better to answer that question.
Okay, gotcha. Okay, next question. is asking, could you explain the physical reason why the ISC is less accurate versus the PMAX?
Non-uniform soiling.
Easy.
In the case of non-uniform soiling, that's where the measurements start to diverge. If there is no non-uniform soiling, then the measurements are very similar.
Okay, perfect. Okay, next question. As a reminder, you can continue to submit questions in the Q&A box. We got a lot of them, so please continue to submit away. Next question, why is the RDE 300i not UL certified for intrinsic safety when it sits at a 1500 volt and has the potential to cause serious bodily harm?
Well, thank you for answering that. It is, Michael, are you there? Would you like to answer this question?
It is UL certified.
Oh.
Yes. It is recently UL certified. We've started shipping units with the stickers, and we have full documentation for that as of a few months ago. So that was a big project for us.
Okay, cool. Okay, going through rest of the questions.
And that being UL 61010 for safety on electrical measurement devices.
Okay. Okay. How does someone correlate the soiling sensors with robotic cleaning systems?
It's a very nuanced question. So what we have to differentiate there is, are you trying to measure the performance of the automatic cleaning robot system? In that case, you really need to have a full-size reference module in the string where the robot is cleaning it. And then compare it to something that's external, such as a reference cell that's maybe automatically washed. There's a lot of challenges to that approach, but we've definitely kind of figured out a good system. If that's something of concern, or you'd like a system like that, we can talk about it offline. Generally, my concern of automatic cleaning robots, which may not be a concern, is that the dust starts to deposit along the edge of the module, but I've been told that that is not the case. But in any case, you really need to perform a measurement off the module, and I'm claiming PMAX measurements to properly assess the performance of those cleaning robots. The other way would be if you want to just measure soiling outside of the cleaning robots, so how much gain you're getting from relative to the performance gain of the cleaning robot while it's cleaning panels as to the environment itself as a baseline. And then you'd want to have an external sensor that's outside of that system, just monitoring the environment.
Great answer. Okay. Next question is about solar panels. What are the maximum module wattages you can use with your device, and are there optional module connectors other than the MC4?
So RD300i operates on modules that are 30 amps and 250 volts, up to 1500 watts. And what was the second question?
Are there optional connectors that you could use other than the MC4?
We only offer the MC4 connectors at this point. It's up to the customer's discretion to adapt those to other compatible connectors, such as the Evolution 2 MC4. Okay,
we have time for just a few more questions. Next question is, with the RDE 300i measurements, are in situ measurements recommended over reference modules?
Yes, because in situ modules they're more representative than closely related to other panels in your PV site. So it's the same wind patterns, the same rain, whereas a standalone offline module may have different wind patterns, causing the soiling pattern on those panels to change differently than if it was in situ. But ultimately, if you have an IV curve-based system on a standalone module, that's also a very good way to do it.
Okay. Next question. It says, it seems like it might be better to mount the RDE 300i 5 modules in anyway, but is the only real reason for backside irradiance?
Yes.
Okay. And then there's a second part to this question. I'm just making sure I'm reading it correctly. For front-facing modules, not bifacial modules, array edge effects are negligible and it's okay to mount at the end of the row, or no?
Yes. Yeah, and I want to clarify, we discussed our module cell based systems. For monofacial modules, as I said with the module cell on bifacial, there's a little bit of uncertainty rear side. But with a monofacial module and one reference cell, the data is equivalent to module. So if you have a monofacial module, I'd highly recommend going with module cell. Because of that fact, there's no non-uniform rear side irradiance. The irradiance on the front side is largely uniform. There's no edge effects as much that can affect your soiling measurement. Of course, the placement of irradiance sensors, there's a lot of studies about where to place those. But for the sake of a comparison between a panel and a cell, you can place them on the edge. Reference cells systems work great.
Okay. All right, well, we'll have time for maybe 2 to 3 more questions. Okay, next question will be, what is the difference in uncertainty between a reference cell pair and an optical sensor?
So it's difficult to say, but if you look at the data that we provided, you can kind of draw your own conclusions. They're very comparable. Like I said, a reference cell or even an ISC reference module-based system is closer to optical than the IV curve-based systems. So we can definitely send some follow-up data about how those relate and compare.
Okay. And then I think this will be our final question. How does the RDE 300i perform IV curves on string-connected modules?
So it's kind of it's the revolutionary feature of RDE 300i in that it can rapidly disconnect the module from the string to perform the IV curve measurement within a small fraction of a second and then reconnect it. This is kind of what enables the ability to measure these string connected modules and one of like our key features of why RDE 300i is important.
Perfect. Okay. All right. Well, that is all the time that we have for questions today. If we did not get to your question, we will reach out to you directly. Please take a moment to fill out the survey that's going to pop up when this webinar concludes, because we do use that feedback to improve our future webinar programming. This webinar will be shared with all registrants, so you can view it again at your convenience. I'd like to thank Josh for presenting and for answering so many great questions, and Kip and Zonin for sponsoring today's webinar. Thank you to everyone for joining us today. Hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you so much. Have a nice day.